Assalamualaikum warahmatullahi taala wabarakatuh. With me, Sir Afif. So we are going to continue our lesson today with lesson 18 in chapter 4, periodic table. At the end of the topic, students should be able to explain the variation in atomic and ionic radii across periods 2 and 3 across the first row of transitions elements and down a group. B. Explain the radius of isoelectronic species. There are four trends of periodic tables. Number one, size of atom or atomic radii. A, atomic size and also ionic size. Number two, ionization energy, IE. Number three, electron affinity. And number four, electronegativity. Okay, this is periodic table trends. So as you can see, okay, as a general, when we say across the periodic table, across meaning that from here, left to right, we say across the periodic table. So here, from up here to down here, we call it as going down the group. So these two terms, okay, we're going to be used in this lesson. Okay, you have to know, okay, what are the trends for across the period, and also what are the trends for going down the group. Periodic trends in the size of atom or atomic radii. The size or radius of atom is difficult to be defined exactly because the electron cloud has no clear boundary. The distance between the two nuclei in a molecule we call as atomic radii. So generally, across the period, meaning from left to right, the atomic radius or atomic size decreases. And when going down the group, the atomic size increases. Two factors that affect the atomic size or atomic radii. Number one, okay, the effective nuclear charge or ZEF, okay, felt by the valence electron, meaning the outermost electron. Okay, this ZEF is used to explain the trend atomic radii across the period. While number two, shielding or screening effect, okay, is used to explain the trend of atomic radii going down the group. So number one, okay, 1 Roman, effective nuclear charge, ZEF. What is ZEF? The nuclear charge that actually felt by an electron because of the nucleus attraction. Okay, so value of ZEF, okay, ZEF is equal to Z minus S. What is Z? Z is number of proton and S number of electrons filled at the inner orbital. Okay, inner orbital, meaning that exclude the outermost orbital or the valence orbital. Okay, more explanation about ZEF. Okay, for example, okay, as you can see in this slide, so we have, okay, phosphorus, okay, with the 15 number of proton, and also chlorine 17 proton. So ZEF, as you can see, okay, ZEF equal to proton number minus the electron in the inner orbital. So ZEF for phosphorus is 15 minus 10, so equal to 5. While for ZEF, 17 is the number of proton of chlorine minus 10. Okay, 10 electrons in the inner orbital of chlorine. So you get 7. So as you can see here, ZeV of chlorine is higher than phosphorus, meaning attraction force between valence electron and nucleus in chlorine atom are more stronger compared to phosphorus atom. So when the attraction force between valence and nucleus are more stronger, meaning that electrons are pulled towards electrons and are pulled towards the nucleus, making the size of chlorine is smaller than phosphorus. Example 4.4. So given sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. All these atoms are located at the period 3. So example, we have atoms, electronic configuration, and ZeV. So 12 mg electronic configuration, 1s2, 2s2, 2p6, and 3s2. So 1s2 until 2p6 are the inner orbital. So 12 minus 10 is equal to 2. So for the aluminium, as you can see, 13 minus 10, equal to 3. And also for silicon, 14 minus 10 equal to 4. And for phosphorus, 15 minus 10 equal to 5. So we can conclude here, across the period, when number of proton is increased, ZeV also increase. More elaboration about the ZeV across the period. Number of proton increase, the effective nuclear charge or ZeV increases. Attraction of nucleus towards the outermost electron also increase. Thus, the sizes of atom decrease. Let's see the second factor, shielding or the screening effect. Value of n increase the larger the orbital. N is referring to the energy level. So electrons in the inner shells shield the electrons in the outer shells from the nuclear charge, meaning it is shielding or screening effect. So going down the group, sizes of atoms increase. This is the example of elements in group 1. As you can see, lithium, sodium, and potassium. So as you can see, lithium have only 2 energy level here, while sodium have 3 energy level, 1, 2, 3. Potassium have 1, 2, 3, 4 energy level, or 4 orbits. So when the number of energy level and increase, the shielding effect will also increase. Why? Because the electron in the inner shell, will shield the outer electron or the valence electron from the attraction of the nucleus, meaning weaker attraction of nucleus towards the outermost or the valence electron, thus making the size of atom increase. This graph shows that down the group, sizes of atoms increase. For example, this is in group 1, and this is the atomic radii of group 17. So we can conclude, for the shielding effect, going down the group, number of proton increase. The shielding effect also will increase. Attraction of nucleus towards the outermost electron decrease. Thus making the sizes of atom increase. So as a picture of atomic radii in the periodic table, you can see in this slide. Increasing atomic radius from right to left. Okay, from right to left, and this one increasing atomic radius, okay, going down the group. Okay, now let's see the periodic trends in the ionic radii. So now we are talking about ionic, okay, meaning it has charge. Okay, the electron are either removed or gained. Okay, this is example of formation of lithium fluoride. So lithium plus fluorine. Okay, and then we will get the ionic compound of Li plus and F minus. As you can see in this picture, as the picture of the ionic radii. Okay, before and after. Okay, cation is always smaller than atom from which it is formed, while anion is always larger than atom from which it is formed. Okay, now let's see why. Why cations are always smaller than the atoms which it is formed. So, okay, when electrons are removed from the valence shell, the electron repulsion decrease. Okay, allows the remaining electrons in the inner orbital to be pulled closer together around the nucleus, okay, making the cations smaller than the atoms from which they are formed. How about anions? Why they are bigger than the atoms that they are formed? Okay, when electrons are added to an atom, the mutual repulsions between them increase. Yes, because electrons carry negative charge. Okay, this causes the electrons to push apart and occupy a larger volume, making the anions larger than the atoms from which they are formed. So these are the comparison of atomic radii, which before the electron is added or removed with ionic radii. So this is after, okay, after it become ionic, electron is added or removed. Okay, so as you can see here, okay, and then this is atomic radii, and in this side is the ionic radii. Isoelectronic series. Isoelectronic series are groups of atoms and ions which have the same electronic configuration. Within the isoelectronic series, okay, the more positive the charge, the smaller the species. The more negative the charge, the larger the species. Okay, so all these ions, okay, are located at the same period, which is period 3. So when all the atoms, okay, become ions like this, so for example Na plus, okay, these cations have the same electronic configuration, which is 10 electron, 1s2, 2s2, 2p6. So look at the charge here. The charge become more positive. Okay, thus the size is decreasing. While for this cation, all of these have the same electronic configuration, which is 18 electron. So it will be 1s2, 2s2, 2p6. Okay, 2p6, 3s2. Okay, 3p6. Okay, so as you can see, okay, when the charge of the negative is increasing, okay, the size also will increase. Okay, across the period, the sizes of cations decrease due to the increase of Z. Okay, ionic radii of Na plus is bigger than Mg2 plus, is bigger than Al3 plus, and bigger than silicon. 4 plus. All these ions, okay, they are isoelectronic, which has 10 electron, meaning 1s2, 2s2, 2p6. All these have this electronic configuration. Okay, thus ZeV increase, ionic radii decrease. Okay, for ionic radii of anion, this anion, okay, they are all isoelectronic with 18 electron. So the electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. So making the ZeV, when ZeV increase, ionic radii decrease. So these are the comparison, okay, the comparison of atomic ionic radii, okay, for each group. So as you can see in this slide, okay, group 1, group 2, okay, group 13, 15, 16, and 17. Okay, so let's answer some practice questions here. Compare the size of atoms or ions below and explain. The first question is between sodium and rubidium. Okay, so both sodium and rubidium, okay, rubidium are in the group 1, but different period. Rubidium, okay, is located below Na. So meaning, okay, going down the group, okay, going down the group, okay, rubidium has more proton or energy level. Okay, it's a proton number. Okay, when it has more proton number, meaning rubidium has, okay, higher or stronger shielding, okay, shielding effect. Okay, meaning, okay, attraction, okay, between nucleus, okay, nucleus towards, okay, valence electron are weaker, thus size of Rb or rubidium is larger than sodium. Okay, so number 1, Rb is larger than sodium. Okay, number 2 is between silicon and sulfur. Okay, both are in the same period. Okay, are in the same period, which is period 3. Okay, but different group. Okay, so when we say about a cross period, okay, in group, this one is group 16, this one is group 14. So cross period. Okay, before that, the ZeV for sulfur, if you calculate, you will get 6, while for Si, you will get 4. So across period, okay, sulfur, okay, sulfur has more proton number, okay, meaning sulfur has higher ZeV, okay, higher ZeV, okay, so attraction between, okay, nucleus towards, okay, towards valence electron is stronger, thus size as sulfur is smaller than, okay, silicon. So as, okay, silicon, okay, is bigger than sulfur, or sulfur is smaller than silicon. Okay, next question is between sodium and also sodium ion, and Na plus. So cation electron is removed. okay, electron is removed. So we can say that Na plus is okay smaller than sodium atom. Why? So when electron is removed, okay, from the valence shell, okay, the electron repulsion, okay, decrease. So when the electron repulsion decrease, okay, the remaining electron are pulled inwards or towards nucleus, making the size become smaller. Next is between Cl and Cl minus. So anion electron is added. Okay, so you can say that Cl minus ion is bigger than Cl, okay, atom. Why? When electron is added, okay, mutual repulsion increase. Mutual repulsion of what? Of electron increase, okay, making the attraction, okay, making the electrons, okay, push apart, okay, and occupy larger volume. Okay, larger volume. Thus, the size of anion is bigger than its atom. Okay, next question. Okay, between Al3 plus, okay, and D3 minus. Okay, both have a charge with number of 3 but different kind of charge. So Al3 plus is the cation, okay, while P3 minus is anion. Okay, for the same reason as like in the previous question, okay, anion, as we know, electron is added, okay, while cation, okay, electron is removed, okay, meaning that, okay, the ion of P3 minus will be bigger than the Al3 plus. Okay, and the next question is between Na plus and Si4 plus. Okay, both ion are isoelectronic series. What do we mean by isoelectronic series? It has the same electronic configuration. Okay, so as you can see, Na plus, okay, 1s2, 1s2, 2s2, 2p6. Okay, Si4 plus also, you have the same configuration, 1s2, 2s2, 2p6. So, okay, the greater the positive charge, the smaller, okay, the smaller the size. Thus, Si4 plus is smaller than Na plus.